everybody remember those equations? All I've done here is just put 0 to 0.8 on there. Will this always be 0? Why not? Why won't the inlet conversion be 0?
Yeah, don't you have like
before the inlet?
You could either have a mixture, that's one way of thinking about it, or a recycle stream, or reactors in series, right? Sometimes you're going to have one reactor flowing right into another. Okay, so again, if you have some table that simply gives you this number for each conversion, you read off that table, and I'm not going to do the math a second time, but now you get 225 decimeters cubed, or about half of what it took for a CSTR. Now, what is that area on this plot?
It's the area under.
Now it's the area under the curve. And that's why a CSTR requires more volume, right? Just look at the plot. It has to. Because you're either going to have the area under the curve or the total area. So obviously it's going to be less volume. Another way to think of why it requires less volume is within each section of a PFR, you can say this is approximately a CSTR, right? Because if you're well mixed radially, then the only thing that matters is that you're not well mixed going down the length of the PFR. But that's okay, because I'm going to take really, really small sections. And I'm going to say all that a PFR is CSTR in series. So I know I'm taxing my little plot here, so I'm going to erase some of this. Radially there is. So this one, this region is well mixed if this delta X is small. Yeah. Yeah, otherwise we couldn't have come up with the design equation that we did, right? We wrote it in terms of length. That's assuming that cross-sectionally everything is well mixed. So if I have a bunch of CSRs in series, these are the areas that I get, right? Like you guys said, X I'm converting, I'm going from one X to another. And so this is just the change in conversion for each reactor. And then of course the conversion's changing, so that puts me up here, and the rates are changing with conversion. And obviously this is just the, I don't remember what it's called, rectangular approximation of differentiation. So again, a PFR is nothing but an infinite series of CSTRs. Okay? So that's why you end up with the integrated form here, which is just the area under the curve, whereas over here you didn't end up with the integrated form, you just end up with the product. Because as soon as you start making products in a CSTR, they slow down the rate of the reaction everywhere. When I start making products in a PFR, it only slows down to the rate of the reaction downstream. So that's why a PFR is faster, because it's able to do the fast rates at low conversions. It's actually able to do them at low conversions. Whereas in a CSTR, as soon as you make that product, it's spread throughout, and it slows down the rate everywhere. So again, for an isothermal reaction, the PFR is always going to require less volume than a CSTR. And it doesn't mean it won't for a non-isothermal reaction, but if you're not isothermal, a lot of weird things can happen, right? Because the rates are going to be different. So just to follow up on this point, we'll do a quick example and then we're going to be done today of two CSTRs in series. Nothing should really surprise you after already seeing that plot, but we'll do an example anyway. So I have some flow in stream 0, right? It hits reactor 1, it has some volume 1. Then we go flow out from 1 into 2. So the inlet of the second reactor is the same as the outlet of the first reactor. Everybody see that? And then we come out of the second reactor FA2. We can define the conversions like that, right? Where this is the conversion through reactor 1. This is the total conversion through both reactors 1 and 2. Okay, everybody remember that equation? No questions there, right? The flow out of the first reactor, flow in minus flow in times conversion. What do I now write for the second? I'm going to put conversion 2 here. Are you sure? Because I said that conversion 2 was the total conversion throughout the system. So if you're defining the conversion as the total conversion, which is normally what you do, this is still FA0. Is that clear why?
It's because you draw in the box around the system. Is that what you're saying?
It's simply because this conversion is a definition, right? And this is saying the moles of A reacted over the moles of A fed. And by fed, it means to the system. And by reacted, it means throughout the system. The 2 doesn't mean the conversion that happens in 2. It just means the conversion that has happened after reactor 2. Another way of thinking about it. So this is the balance for reactor 1, but this is the balance for reactors 1 and 2. Okay, so if we rearrange and we do the material balance on reactor 1, same equation that we already had. Okay? The volume in reactor 1 is equal to the flow rate in times the conversion divided by the consumption rate.
The FA not.
No, I think that's correct. Because you move it over, but then you divide by minus R. So it's the same as moving these over. All right, so now though for reactor 2, right? We have flow out minus flow in minus the generation term. In this case, consumption of A. And so rearranging that, you get a different equation. This is the part that you got to kind of keep your ears perked up to. You still get the flow rate into the total system, but now I can't put x2. What do I put instead? That's right, x2 minus x1. So on our plot, we have the final conversion, 80%, right? And now we have another design equation. What is it? What's the other thing that we can control here? Flows, flow rates. But that doesn't show up on a Levenspiel plot. What do I need in order to draw these two reactors on that Levenspiel plot?
X1.
Yeah, you have to determine how much you're going to let it convert in the first versus the second, right? You still have a choice. So if I make x1 40%, it's right here in the middle. And so what's x2 minus x1 is 0.4, right? And then it's 0.4 times 1 over the rate. And you get that area. Which area is that? Yeah, remember though that it's V2 over FA naught, right? It's not just a volume. You still have the flow in there. And now the first reactor is this other part. So is it less volume or more volume than a CSTR? Less. And of course, maybe I should have done it the other way, but it's hard not to jump straight to the infinite series when you're talking about an integral. If I keep adding CSTRs, right, you get right back to a PFR. An infinite number just gives me the area underneath that curve. But again, I would have to tell you what this intermediate conversion was. The other thing, though, that I could tell you, right, is I could tell you what a desired ratio of volumes would be. And then you could determine at what conversion would you get that ratio of volumes. Right? As I change this intermediate conversion, the ratio of volumes between the first and second reactor also changes. Okay, any questions? Okay, last thing we're going to do is, what would this look like for a series of PFRs? How does my Levenspiel plot change? I'm still at 80%. Right. So it's the same as a single PFR. So is there any reason to ever have two PFRs back to back?
One goes back.
Only if I'm doing something with those streams in the intermediate section, right? It could be a recycle. I could be splitting off some product because maybe my product's inhibitory, so I want to send some of it to a, in other words, in between here I might run it through a distillation column or some sort of separator, or I might try to do a recycle. But yeah, if I'm just going straight from one to the other, there's no reason to split it into two units. All right, that's it for today. Homeworks will be posted by the end of the day, due next Tuesday, not next Thursday.
You gonna post solutions to the first one?
Yeah, I was just waiting until you guys got them back.
Okay.